Imagine you take a projectile and you launch it horizontally with some initial velocity. It falls down to the ground, and it moves along a curved path like this. While it's in the air, the horizontal velocity never changes. The reason this doesn't change is because gravity doesn't pull left or right, gravity only pulls down. So we don't speed up horizontally and we don't slow down horizontally. What about the vertical velocity? We start out with no vertical velocity because we push this thing horizontally. We don't push it up or down. But once it's in free fall, it accelerates downward because gravity pulls down. And so those vertical velocities change. Specifically, we speed up in the vertical direction. We could then draw the two-dimensional velocity here, here, and at every moment by connecting tail to tail and tip to tip. Now let's take a look at projectiles launched at an angle with some initial velocity. It goes up before coming back down. Because we launched this projectile at an angle, the initial velocity has an x component and a y component. Just like before, the x velocity never changes as it's in flight. We don't speed up or slow down horizontally because gravity doesn't pull left or right. Vertically, though, there is gravity, and so this vertical velocity will slow down initially. It stops at the very top. There is no vertical velocity at the top. And then we speed up vertically as we descend. We can again draw the two-dimensional velocity vector by connecting tail to tail and tip to tip, and we do that for every moment that's shown. Now let's take a closer look at the math behind these two examples. Here's the first case launched horizontally, and here's the second case when we're launching at an angle. I'm going to go ahead and draw in the x and y components of this initial velocity, vx, and the initial y velocity. Why haven't I drawn this as vix? Why am I not calling this the initial x velocity? Well, the reason is because the velocity doesn't change on the x-axis, so there's no need to describe the initial because it's the same as the final. So we don't put the initial there at all because there's only one value, vx. Over here on the left side, this initial velocity doesn't really have components because it's not going up or down. In other words, all of the initial velocity is on the x-axis, and none of it is on the y-axis. On the other side, that's not the case. We have to calculate the components using cosine and sine. So the x component is adjacent to theta, and because it's adjacent, we use hypotenuse cosine theta. The y component, the y leg of the right triangle, is opposite theta, so we use vi sine theta, or hypotenuse sine theta. Notice the difference between the left and right examples. That's going to have a really big impact on the equations we use when we solve problems involving projectiles. So let's start out by describing the x and y axes in equations. The x-axis has constant velocity. We're not speeding up or slowing down horizontally. The equation for constant velocity is this. Vx, the constant velocity, is the displacement over time. On the y-axis, though, we are accelerating, and so you can't use the same equation. We can't apply this to the y-axis. We have to use the equations for constant acceleration, and those look like this. The first thing we have to do, though, we're applying this equation and this equation. We're applying all of these to the y-axis. So for example, right here when we say vi, we're talking about the initial y velocity. And right here when we say vf, we're talking about the final y velocity, because only those y velocities are accelerating due to gravity, ag. So how do I specify that this is the y-axis? That we're discussing the y-axis in these equations? We add a subscript y to here, to this velocity, and to every velocity that appears in these equations. Then we're going to start with the exact same equations for projectiles launched at an angle, because we have the exact same scenario. There's constant x-axis velocity, and there is a constant y-axis acceleration. The difference is what we plug in for Vx and Viy. So look back to the top, and then look over here. On the left side, Vx is equal to the initial velocity Vi, and the y-axis initial velocity, these velocities are all 0 initially. On the right, when we launch our projectile at an angle, the situation is a bit more complicated. Vx doesn't equal the initial velocity. Only part of the initial velocity, the cosine part, only part of the initial velocity is on the x-axis. So this is Vi cos theta. And in these equations, the initial y velocity is not 0. It's the vertical part shown by this upward arrow. And that vertical part equals Vi sine theta, according to the right triangle. So for every one of those Vi's, we replace it with Vi sine theta. When we plug these things in, make these substitutions, here's what the equations look like. And these are the equations that you get on your equation sheet. The thing you have to remember is that you have to go to the equations with theta, theta, theta. These all have theta, and we have to use those equations when the problem involves a projectile launched at an angle. When the problem involves a projectile launched horizontally, you have to use these equations. Now finally, we're going to learn just a couple tricks for projectiles launched at an angle. Let's say you have a scenario where you start the projectile from the ground and you launch it with some horizontal and initial vertical velocity. It goes up and it comes all the way back down to the ground. In this case, there's a trick. Your vertical displacement is 0 because you do not go up and down on the hole from your start to end point. On the hole, you are not going up or down, so your vertical displacement is 0 meters. Next trick, if you launch a projectile with some horizontal and initial y velocity, and it goes only up to the peak, well, something happens at the peak. At the peak, the velocity is entirely horizontal, and the y velocity, the vertical velocity, is 0. We're not going up or down, we're only going horizontally at the peak. So that's a piece of information that you have to use. They won't say the vertical velocity is 0. You just have to know it and remember that this is what you use when you see at the maximum height or peak height. Okay, another one. If you take your projectile, launch it with an angle, it goes up again to the peak, they might ask you, find its peak height. And what that means is find the final y velocity. But we can't find the y velocity using the acceleration equations, because those equations don't have y final, they have delta y. So you have to use this equation to get y final. Now it turns out it's really easy. What's your initial position? You start at the ground, so initially you were 0 meters up. And so delta y simply equals your final position. And the last trick, you launch a projectile at an angle, it goes up and then back to the ground, but you launch it from some initial height. If they say find the initial height, they mean find the initial y position. How high up is it from the ground at the beginning? Now again, y initial doesn't show up in any of those acceleration equations. So you can't just look for y initial, you have to find delta y. How do you get y initial from delta y? Well, the final position is what? It's 0 because we're 0 meters off the ground. So if you take the negative of both sides, multiply both sides by -1, you get this. And after you calculate delta y from an acceleration equation, you can then just make it take the negative of delta y, and that will give you the initial height.